We're still in section 8.1. This video is titled Finding Arc Length. Our objective here is to apply the arc length construction that we just developed to find the length of a variety of curves. So fair warning, these integrals can be pretty hairy because of the nature of the integrand that we have. It's a square root of a 1 plus a derivative squared. So it can get pretty nasty, but we're going to work through them carefully. Our first example is pretty standard. So we have a length of a curve that we want to find. The curve is expressed as a function of x given over an interval from 0 to 2. So if we have our function expressed this way, we can go ahead and find the derivative pretty handily. The 1 goes away. Bring down the 3 halves in front of the 6. And then x, reduce that power by 1, so 1/2. So this will end up being something along the lines of the 2 and the 6 cancel to make a 3. This is 9, x to the 1/2. Then that length is the integral from 0 to 2 of the square root of 1 plus 9x to the 1/2 squared dx. So what happens with this integral, the x to the 1/2 squared becomes x. And then we have 1 plus 81x dx. Okay, so what do we have here? We have an integrand that has a linear function of x. So what we might find helpful is letting u be 1 plus 81x. du will become 81 dx. So when we replace that back in, we're going to divide by 81. And we can go ahead and change the limits of integration already if we want. So u of 0 becomes 0 times 81 is 0 plus 1. And then u of 2 becomes 81 times 2, which is 162, plus 1, which is 163. Then we get the integral from 1 to 163 of 1 over 81 times the square root of u du. And so if we pull out the 1 over 81, we recognize the u to the 1/2 being the replacement for square root of u. Sorry, that should be 3. Then we got 1 over 81 times 2/3 u to the 3 halves from 1 to 163. So we get 1 over 81 times 2/3 times 163 to the 3 halves minus, and then if you plug 1 into that, you just get 2/3. So you can go ahead and pull out the 2/3 there. You get 2 over 3. 81 is already 3 to the 4th, so we actually end up with 3 to the 5th. However you want to write that. Times 163 to the 3 halves minus 1. And 163, you should check if that's divisible by anything. Probably not. Use whatever techniques you have to verify that. So going through the first few primes from 1 to 30 should do it. If it's not anything like that, then you're not going to find anything. So that means this is as simple as we can really write it without getting into inexact forms. So I would leave it like that. All right, let's do another example. But what if we're integrating with respect to y? As we often do, find the length of the curve from 1 to 9 for y of this curve, x equals 1/3 square root of y times y minus 3. So it's already expressed in terms of y. And we're just going to have to write briefly, which we can derive it in just the same way as the original formula, but you can just take my word for it that it works in the same way if you're expressing it as a function of y instead of x, that the length of a curve as a function of y can be written as the integral from c to d. So in this case, our limits of integration for y of the square root of 1 plus g prime of y squared dy, where g is the function of y. So in this case, our g of y is the 1/3 square root of y minus 3. And we can go ahead and write that more simply as 1/3 y to the 1/2 times plus 1 gives us 3/2 minus 1/3 and the 3 cancel, so we just get y to the 1/2. So if we derive that, g prime of y, bring down the 3/2 and you get 1/2 y to the 1/2. Bring down the 1/2 and you get minus 1/2 y to the negative 1/2. Okay, then that is what we'll plug into the expression for g prime of y. And now we can find the length, the integral from 1 to 9, the square root of 1 plus, and then our expression was 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. Is that right? Yes, that was a negative. Okay, cool. Then we're going to write, okay, so that's squared, all under the square root dy. Okay. Carefully, we're going to perform the binomial operation here. So multiply this out. We get 1/4 y to the 1/2 times 1/2, or y to the 1/2 times 1 to the 1/2 is just y to the 1. And then the middle terms, we're going to have a minus 2 times 1/4 y to the 1/2 plus negative 1/2, that gives us nothing. Those cancel out. And then the last one is going to be y to the negative 1/2 times y to the negative 1/2, so it's going to be plus 1/4 y to the negative 1, y to the negative 1. Okay. So that is that expression simplified with the, now that we've squared that binomial. And now we just clean this up to make it something manageable. So we're going to get, I'm going to express it as a polynomial slash rational. So I'm going to put the 1/4 y in front. And then 1 minus 1/2 is going to give us 1/2. And then the expression with 1/4 y to the negative 1, that's going to be the same as plus 1/4 y. And so that's what we have there. And so you'll notice that this is, oh boy. So we have inside the square root, we have a linear part plus a rational part, all underneath the square root. So what can we do here? We can try to rationalize. So we're going to try, let's start with doing a substitution. We're going to let u be the part inside the square root. So it's going to be 1/4 y plus 1/2 plus 1/4 y. Sorry, 1/4 over y. And then du would be 1/4 minus 1/4y squared dy. Okay. The only issue here is we do not have a y outside the square root. And so if we wanted to replace dy, we couldn't do so without leaving behind a y squared. And so this might not work. But no matter. The other thing we could do is we can try some other thing where we take this polynomial, we actually combine it into a rational expression. So we're going to combine it all into one rational expression. So I'm going to have, what's the least common denominator here? 4y. So multiply the first term by y over y. So y squared over 4y. The second term by 2y over 2y. The last term is fine. Okay. So this is where, we're on the fly discovering what techniques of integration we need to use. Some techniques you try out may not apply to that specific expression that you're working with. So in this case, though, I end up with y squared plus 2y plus 1. That is going to work out nicely because I'm going to get a square, something squared on the top. So I'm going to get y plus 1 squared over 4y underneath the square root. Okay, it's working out nicely. This is a lot nicer than what we had before. So everything is positive here because we're working for y values from 1 to 9. So I can just pull that out as a y plus 1 in the numerator. Y plus 1 times the square root of 1 over 4y dy. Okay. And now, so I'm going to convert that 4y. So this is going to be, so that 1/4 obviously comes out as 1/2. So 1/2 integral from 1 to 9 of y plus 1 no, what's going on here? For some reason that won't go away. Anyway, y plus 1 of square root of 1 over y dy, but I can write that as y to the negative 1/2. And then I can distribute the y to negative 1/2. Okay, so this was the way to go. So simplifying the expression inside, that was the way to go here. And now it's gonna give us something very nice. So I'm gonna end up with a L, the length equals 1/2 times the integral from 1 to 9 of y times y to the negative 1/2 is y to the 1/2 plus 1 times y to the negative 1/2 is just y to the negative 1/2 dy. Okay. Lastly, if we're going to perform this integration, then we have 2/3 y to the 3/2. And then that's going to be 1/2, so 2 y to the 1/2, evaluated from 1 to 9. Okay, then we have 1/2 times 2/3 times 9 to the 3/2 plus 2 times 9 to the 1/2, which is 3, minus 1/2. Sorry about that. 2/3 times 1 to the 3/2 is just 1, plus 2, yeah, that's that. Okay. Okay, not bad. Then 9 to the 3/2, by the way, is 9 times 9 to the 1/2, which is 3, times 2 over 3, plus 6. Okay. And now we just clean up the algebra here. So 2 plus 2/3 is going to be 8/3. Here we get some nice cancellation. So we end up with, oh, and of course the 1/2 is going to cancel it. That's going to make a 3. Those are going to cancel. And so we end up with a 9 plus 3 minus, cancellation here again, that's 4, minus 4/3. 12 minus 4/3. And times 3 over 3. That means it's 36 over 3. Minus 4 is 32 over 3. That's our answer. So not terrible. The hard part here, of course, was getting this into an integral that we can actually tackle, right? So this one was, it was a little longer. But the general techniques then is, again, we are going to have to perform, the integration techniques that we've discovered and loved, or maybe not loved. And there's going to be cases where, we're not going to be able to apply, the techniques we want. So just as a brief illustration of when we would resort to other techniques, right? So for instance, in this example, we're going to use Simpson's rule. So, and I'm not going to finish the example because, calculation is so tedious. But I'm going to set up the calculations that you need to get. So we're going to estimate the arc length of y equals ln of 1 plus x cubed from 0 to 5 for x. And so what this really means is we would theoretically, want to calculate the integral, but we can't here. So, and that's because notice that y prime, or the derivative of f of x, is equal to derive 1 plus x cubed over 1 plus x cubed, which is equal to 3x squared over 1 plus x cubed. And when we plug that into the formula, right, so literally L is equal to 0, the integral from 0 to 5 of the square root of 1 plus 3x squared becomes 9x to the 4th. And then 1 plus x cubed squared. Well, can't do too much about that. We're going to leave that as that. Okay. So then the idea here is, oh, and by the way, when you're setting this up for Simpson's rule, since you're using a calculator, calculators are terrible at division. So, but by that I mean you're more likely to propagate error. So what you want to do is, in this case, you want to just simplify this by multiplying it as 1 plus x cubed squared Wait, is that what I want to do? Well, you're not going to have much of a choice, so never mind. So when you have that, then your task then would be to set up the integrand for Simpson's rule. So for Simpson's rule, we have n equals 10, which implies our x sub i's come from the set starting from 0 and then up to 5 with 10. So you're going to be adding 5 divided by 10 each time. So 0.5, 1, 1.5, 2, dot, 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 all the way up to 5. So there should be 11 values there. And you're going to find your f of x sub i's using f of x is the square root of 1 plus 9x to the fourth over 1 plus x cubed squared. Find each of those f of x sub I values by plugging in those x sub i's. Form your table. Apply Simpson's rule. And that will be your approximation to the arc length. All right, so in the next video then, we're just gonna round out this section by talking about the arc length function, which means because arc length is always defined using a starting point and an end point,